Here we are at Big Idea 2. This is going to be part 3. So in part 3, what we're going to be looking at is the concept of intermolecular forces. So intermolecular forces. Now intermolecular forces are the sort of the guiding principles behind why molecules stick together. So, you are probably all in a room or in some sort of place right now, and in that place you probably have all three states of matter easily recognizable. I'm sure you have gases, right? And so those molecule gases are flying all around you, so you have the gas in the room. And then you probably have, in one way or another, you have some liquid in the room, right? And then you also have solids, maybe you're sitting at a table or a desk or something like that. So how is it that in the same room you have all three states of matter? The temperature of all these three things will probably be the same because they're all in the same place. The reason why this gas is a gas and this liquid is a liquid and these solids are solid is because of different intermolecular forces. So intermolecular forces, inter means between, molecular means molecules. So this is the forces in between molecules. So as I look at the molecules here in the gas in the room, there's hardly any forces holding them together between them. And so they're gas, right? So they're flying all around. There's no attraction between them at all. As I come to the liquids, there's something attracting these molecules to each other. So they come closer together and stick to one another, forming a liquid. As I come to the solids have a very high force of something holding them together so that at room temperature, they don't even want to budge. They want to stay connected. And so these are all intermolecular forces. And so we're going to go over all the major intermolecular forces and how they work to hold things together. And then that helps to explain why we have all different states of matter at the same temperature. And then also explains then the idea of what are boiling points? Are they high? Are they low? Are these very strong bonds? Are they not strong bonds? And so obviously the forces that hold them together are going to govern all of these things. So that's intermolecular forces. So first of all, to understand intermolecular forces, we have to understand a thing called the dipole moment. So what the dipole moment is the idea of how strong is the particular polarity of the molecule, right? So we talked about polarity in the last one, which is the idea that there's unequal sharing. So one end is negative and then the other end is positive. Well, if you have this situation where there's unequal sharing in which one end of your molecule appears negative and the other one appears positive, then you have a what we call dipole moment. And the dipole moment is symbolized by this blue arrow right here, indicating that there's a difference between the two ends of this molecule, one end being positive and the other end being negative. Now, if you look at this molecule right here, it's got a positive center, two negatives on the outside. The dipole moment then, or the direction of the dipoles is equal in opposite direction, meaning there's nothing to show for it. They've essentially canceled each other out. So this has a dipole moment of 0. So this is a 0 dipole moment, whereas this dipole moment, indicated by this blue arrow, is something of a little bit greater value. So if we look at dipole moment, kind of two rules emerge, and that's basically that the greater the charges are at the ends, so greater charges at ends. So, essentially the higher I have negative here and positive here than at ends, then the greater the dipole moment. And then also the distance between them. So if you were to have a greater distance between the charges, then the greater the value of the dipole moment would be. So the further I get these away from each other, the more I have a very definite positive and negative. So if my positive and negative are right on top of each other, they tend to cancel each other out. But if I move these things way, way, way apart, so if I have a molecule that spreads these out, it's going to be very, very much a definite positive and negative end. Therefore, dipole moment is linked to the size of the charges, which is linked to the differences in electronegativity, and then also linked to the distances between these charges at either end. All right, so let's look, for example, here at a couple of different molecules. So look at here. There's no net dipole moment here because we don't have any differing charges on any ends right here. Now this one right here, of course, this is probably chlorine. So this right here is going to be chlorine, right? Put a little Cl right there. And chlorine is highly electronegative. So it's going to pull the negatives here. So we have kind of a negative end here. We have positive ends here. And so if we were to measure the total dipole moment, here it is, 1.92 is a dipole moment. And we see it symbolized right here. Here's another one with a dipole moment right here. But we have two chlorines. We have one here and one here, which means that they're going to equally pull here. And so here's where our negative charges are going to be centered right here. And if you'll look at that, the charges then are closer together. The negative and then the positive are going to be closer together than they are to say here. So this is a greater distance. And remember, with a greater distance comes a higher dipole moment. So here we see a very similar molecule with a closer distance, a lower dipole moment. Over here, similar kind of thing. Now that we add 3 chlorines right here, we're going to have an even closer distance. So this right here, essentially the negatives are going to have to be, centered in between these 3. So somewhere right in here, but these are kind of like spreading out further and further. And so this centering becomes closer to this positive charges. So we have an even closer here. Hopefully with my scribble circles, you can see how this one's smaller than this one, this one. So this one definitely has lower. 1.04 is a dipole moment here. And now on this one, as soon as we add a 4th one over here, now we're not pulling anything any particular way because all of these have an equal pull on each other. So the dipole moment here went to 0. So hopefully that helps to understand dipole moment. So as we understand dipole moment, then we start to get into the intermolecular forces that hold everything together. I wanted to put this up just to begin with because the hardest thing we know of is a diamond. Now, a diamond is very hard because of its intermolecular forces. Now, what happens in a diamond is what we call network covalent. Okay, so this is called network covalent bonds. Now, this is going to be the hardest and best of all of the intermolecular forces to be a network covalent bond. So essentially what happens in a network covalent bond is that you form some sort of a lattice of molecules held together. And so essentially it becomes one big gigantic molecule. And so there's actually sharing of electrons in a sense between these little links in the lattice. So this is a diamond, this is graphite, and this is silica. And the reason that I put these up here is that these are the exact same molecules, but graphite, which essentially is pencil lead, is way easier. Oops, that should be an A right there. Is way easier to break apart than your diamond. So why is a diamond so hard? The reason for that comes in the fact that when you look at how complex and interconnected these lattices are, there's no easy place to cut this. It doesn't seem to want to break. You can't find a plane that will break across this at all. You're always going to run into an actual molecule. But if you look at graphite, it easily separates here. So when you're moving your pencil along your paper, what's happening is it's easily breaking along these lines, whereas these particular ones here are not going to break apart, and that's what has actually left you with your line on your paper. So that's actually hopefully that actually explained to you why diamonds are so hard and why graphite isn't, even though they're actually made of the exact same molecules. So they're all just carbon atoms. This is silicon or silica. And so a silica is going to be silicon and oxygen atoms together, and this is what makes up quartz. So quartz, similar to a diamond, has kind of a complex network right here that holds these all together, and that makes it a fairly hard thing. So silica, quartz are very difficult. to separate. So these things will have super, super high boiling points, because what's it going to take to free these or break these apart from each other and turn them into the next phase of matter? It's going to take a lot, because these are connected in a very, 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 very strong way. So these are called network covalent solids. So at room temperature, these are the ones that are always going to be solid no matter what you do. All right. So let's look at some of the other ones. Here we have your typical dipole sort of interactions. So this is water with an ion dissolved in it. So a sodium ion is going to have a positive charge. Well, the back end of all your water molecules is going to have a negative charge because it's polar. So ion, so here's your ion, the sodium right here. Right, here's your ion. And it's surrounded by the negative end of all your dipoles. So this is an ion-dipole interaction. So there's going to be an attraction here, and this is essentially why all salts dissolve. Or, so say you're wondering, why does a salt dissolve in water and completely disappear? Well, this is why. Because of this attraction here, it is surrounded by the negative ends of the water molecule with the ion right there. So this one right here, H bond or hydrogen bond, occurs whenever hydrogen, and here's hydrogen right here. Hydrogen is the result, is what's causing the bonds between two molecules. So this is methanol right here. So methanol will actually go into water and will sort of dissolve or disperse within the water because the hydrogen end of the methanol will connect to the oxygen end of the water. The best example I like to show of this is right here with the DNA molecule. So our DNA unzips and rezips, and the reason why it unzips and rezips so easily is because it actually has hydrogen bonds that occur in between the bases of our DNA. So you'll see oxygen, hydrogen, oxygen, hydrogen. So this is what happens. So as you come along, these are basically just magnetic connections, or we call them electrostatic connections. And they're based off the fact that this oxygen molecule is negative, right, sticking out here. So this oxygen molecule right here will be negative, and this hydrogen molecule right here will be positive because of their dipole nature. All right? So that's a hydrogen bond. Dipole occurs between any two molecules that have both a positive and negative end. So if you look here at this methanol molecule, the methanol molecule has a positive and negative end. And this chloroform molecule also has a positive and negative end. So methanol and chloroform will dissolve in each other because of their dipole nature. Water is also this way. So water, of course, has its positive, negative end. And then if you put another water molecule, it will arrange itself like this. And so this positive end connects to this negative end. And so dipole, you can see hydrogen bond is a dipole interaction, but there's other dipoles other than ones dealing with hydrogen, although most of them are. And so dipole is when any two molecules that are both polar stick together. And then we also could have ion-induced dipole, whereas you have a molecule like this, which is normally not a dipole, but if you get a chlorine that comes close enough to it, essentially what that chlorine is going to do is it's going to attract the positive aspects of this molecule to itself and push the negative ones away. So this ion is strong enough to essentially cause this to become a dipole. So that would be ion-induced dipole. We also have dipole-induced dipole. So you can have a really strong dipole molecule that has a real strong positive and negative end that comes close to a normally nonpolar. And because of this negative right here, essentially it repels the negatives on this, that repels the negatives away to this side. And when it repels it, it leaves the positives on this side. So then this can dissolve in this. So acetone is a very strong dipole, and so it will do this to other molecules like this. And then the last of all, we have dispersion forces. Now, dispersion forces, also called London dispersion forces, are the weakest of all the intermolecular forces. So most of the gases that are always gases at room temperature have a very, 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 very low boiling point. are going to be London dispersion forces. And a London dispersion force essentially says that because of the random interaction of electrons in here, every now and then, because of randomness, electrons will congregate themselves maybe over on this side, leaving this temporarily positive and negative. And then this one over here might randomly do the same thing, where it ends up becoming positive over here and negative over here, and then allowing these to form temporary dipoles. So that's what dispersion or London dispersion forces are. So London dispersion forces always occur between normally non-polar molecules. They're very, very weak, very, very momentary. The only way to make them actually last is to cause so much pressure in between these that you shove them together enough where the negatives from this side push the negatives from this side over. And so with something like nitrogen gas, you can cause it to become a liquid by super pressurizing it. But any one given moment, any nonpolar molecule might have an unequal distribution of its electrons. Therefore, it would have this temporary dipole-dipole situation. Okay, so anything that is depending on London dispersion forces is going to have very, very low boiling point. Anything that's like this, that is a typical dipole will have a fairly high boiling point, depending on where it is. I mean, water, we know that water boils at 100 degrees Celsius. It's a real common dipole. Some of the alcohols boil at lower and such. And then something like this, let's see if we can get that. Something like this, where did it go? There it is, like diamonds. You can imagine how high a diamond's boiling point is. So if we've got like a diamond right here, a diamond, has a super high boiling point because these attractions are so strong. So the strength of the intermolecular forces actually will determine or will guide our what we call boiling point. So how much energy does it take to change it into a gas from a liquid or a liquid to a solid and such like that. So anyways, that hopefully that explains to you all the different types of intermolecular forces and what a dipole moment is and how that integrates into all the things that we see around us. So this right here actually is going to basically describe all of the atoms we see around us, and you can fit them into any of these categories right here, as long as you include that network covalent that I showed with the diamond and the graphite.